Myself Pradip Mandal, Assistant Professor of School of Applied Science and Humanities, Haldia Institute of Technology, Haldia, West Bengal, India. In this lecture video, I will discuss about group theory. Group theory is basically a mathematical system that are composed of a non-empty set together with a binary composition, defined on this set so that certain properties hold. We already known about set theory. Set theory basically a well-defined collection of distinct objects. And in this lecture, we do not discuss details about set theory. Just the following notation we used in this lecture video. First, set of all integers. Second, set of all natural numbers. And Q, the set of rational numbers, the set of real numbers, and the set of complex numbers. So, first we discuss about binary operation. What is binary operation? First we consider G is a non-empty set. Then a binary operation star is nothing but a mapping from G cross G to G. A function from G cross G to G. Then that means for any order pair x, y, where x and y are elements of G, that assigns a third element of G. For example, plus is a binary operation on the set of integer Z. That means if we assign any two number 2, 1, then this plus under binary operation plus this assigned to a number 3. Similarly, if we consider any other pair of number like 3, 5 or any other, then this must be assigned another number of Z. Therefore, plus is a binary operation on Z. If star is a binary operation of an only non-empty set G, then we write x star y instead of star x, y. Where x, y in G. Since the image of binary under the binary operation is a subset of G, we call this G is closed under the binary operation here star. Now we define when binary operation is associative and commutative. For associative property, a binary operation star on a set G is said associative if the condition this hold. If the condition this hold. That means first we apply binary operation A star B, then apply on C. That equals to first we apply B binary operation C, again A star of this for all A, B, C in G. For example, plus is associative binary operation on Z. But if we taking subtraction, then this is not a associative binary operation on the set of integers. For example, for this case, for Z, this property always hold for any integer number. A plus B that equals to A plus bracket B plus C that equals to first we append A plus B plus C. But if we taking subtraction, then we consider three number -2, 4 and 6, all are integers, then the left hand side this equals to -2, -4, -6 that equals to -12, but right hand side equals to -2 plus 2 that equals to 0. Therefore, for subtraction, this condition, associative condition does not hold. That means subtraction is not a associative binary operation. Second example, a binary operation star on a set G is commutative if the condition this hold A star B that equals to B star A for all A, B in the set G. For example, Z, plus is a system where plus is commutative. For integer, if we taking any two integer, then addition of these two integer is always same. If we add first 2 plus 3 and that equals to 3 plus 2, this always same. And therefore, for any integer, this condition always satisfied. Therefore, Z, plus, here plus is a commutative binary operation. Now taking another example, M2 bracket R is the set of all 2 cross 2 matrices over R. And we write down this matrix in this form. M2R second bracket A B C D, where A B C D are in the set of real numbers. Now taking two operations, plus and dot. Plus be the usual matrix addition and dot be the usual matrix multiplication. Then these we know matrix multiplication and matrix addition on of any 2 cross 2 matrix over R is also a 2 cross 2 matrix over R. Therefore, this plus and dot matrix multiplication and matrix addition are is a binary operation on M2R. Now we also know for matrix addition this condition always hold. If we taking any three matrices A, B, C, then this property always hold in matrix. And similarly, A plus B that equals to B plus A always hold in matrix addition. And therefore, plus that means matrix addition is associative and commutative. And we also know this property hold. That means if we multiplication A dot B to matrix, again multiplication another matrix C, that equals to A multiplication of first two multiplication B cross C. This must be same. But this matrix multiplication for any two matrix A dot B, that not always same equals to B dot A. Therefore, matrix multiplication is associative but not commutative. Now we define semigroup. A non-empty set G with a binary operation star, write down star, is said to be semigroup if the binary operation star is associative. That means the condition is hold for all A comma B in C. For example, Z comma dot is a semigroup. Here dot is the usual multiplication of integers. And we know if we multiplication any two integer, then this must be also an integer. Therefore, this dot that equals to multiplication of integers are a binary operation. And similarly, we know this condition always hold in set of integers. Therefore, Z comma dot is a semigroup. Now we define monoid. A semigroup G comma composition star is said to be monoid if there exists an element E in G. We call this element is the identity element such that the condition this hold. That means A star E that equals to A, that equals to also E star A equals to this for all element A in G. For example, the semigroup Z comma dot is monoid, and we already know Z comma dot is semigroup. Another condition, if we taking 1 dot A that equals to A dot 1 that equals to A for all integers. And therefore, here 1 is the identity element. Now we define the definition of group. Let G be a non-empty set and let star be a binary operation on G. Then the pair G comma star is called a group if the following three conditions satisfied. First condition, for all A comma B comma C, the condition this hold. That means associative property holds in G. For second property, there exists a element E we called identity element such that the condition this hold. That means existence of identity element in G. And the third condition, that means for any element in G, there exists another element B in G such that the condition this hold. A star B that equals to identity element equals to B star A. That means existence of inverse in G. In addition, if we taking any two element A comma B in G and the condition is satisfied A star B equals to B star A, then we also call this G comma star is a abelian or commutative group. Okay. Then if any non-empty set with binary operation star satisfy first three conditions, then we call G comma star is a group. And in addition, if we condition this commutative property, then we call G comma star is a commutative or adjoint group. Now, in any group G comma star, the set G, if their set G is finite, then the group is called finite group. And if the set G is infinite, then we call the group is infinite group. And the number of elements in a finite group is called the order of the group. And we denote this order by order of G or G this symbol. Now we are taking an example. The set of all integers Z is abelian or commutative group under the binary operation plus. And we already know plus is a binary operation on Z, and here we already know JD plus is associative on Z. Now 0 must be in G, 0 and for all integers A in Z, A plus 0 that equals to 0 plus A that equals to A. Therefore 0 is the identity element, and for in all element A in G, we also get a element minus A in G, Z minus A in J set of integers, where A plus minus A that equals to minus A plus A that equals to 0. So therefore minus A is the inverse of A. So hence Z comma plus is a group. And therefore first three conditions satisfy: associative property, identity property, and inverse property. In addition, we also know A plus B equals to B plus A for all integers A comma B. And therefore plus is also commutative. Thus Z comma plus is a commutative group. Similarly, we also prove that C comma plus, set of all complex number with binary operation plus, set of all real number with binary operation plus, set of all rational number with binary operation plus forms a group. But if we taking set of all natural number with the binary operation plus, this may not be a group. This is not a group, since n comma plus there is no identity element. We cannot find any element, any identity element. Which property, like this type of property, A plus E that equals to E plus A that equals to A. So therefore n with the binary operation plus is not a group. Now we are taking a finite group example. Problem: so that the all roots of the equation x to the power 4 equals to 1 forms a commutative group under the operation multiplication. Then first we are taking the all roots, then x to the power 4 equals to 1 equation, and therefore the roots are x to the power 4 minus 1 that equals to 0. This is the equation. And therefore roots are x square plus 1. We first taking x square plus 1, x square minus 1 that equals to 0. From this equation we know that the roots are plus minus 1 and plus minus I. And therefore the set, the non-empty set is G equals to 1 minus 1 I minus I. And the operation are the multiplication operation. The first we form the following composition table. In first row we write down the elements 1 minus 1 I minus I, and similarly first column we also write down 1 minus 1 I comma minus I. Now dot is the multiplication operation, and therefore 1 dot 1 equals to 1 we write down here. Similarly 1 dot minus 1 equals to minus 1 we write down here. 1 dot I equals to I we write down here. 1 dot minus I equals to minus I we write down here. Similarly minus 1 into 1 that equals to minus 1, minus 1 into minus 1 that equals to 1, minus 1 equals to I equals to minus I, minus 1 equals to minus I that equals to I. Similarly, we also write down this here. Then from this table, it is clear that the multiplication of any two element of the set G is also an element of G. And therefore, the dot multiplication operation is a binary operation G, and we also say that this means G is closed. Now second property, the associative property. If we taking any three element from here, we for example we taking 1 I and minus I. So 1 dot I dot minus I that equals to I into minus I, that means minus I square that equals to 1. Similarly 1 dot I dot minus I, I dot minus I, that means I dot minus I that equals to 1, 1 dot 1 again 1. Therefore, associative property hold for the element 1 I comma minus I. Similarly, if we taking any three element from this set G, we show that the associative property holds. Therefore, the multiplication is associative. Again, from the table we clearly see that 1 is the identity element. Why? And 1 into 1 equals to 1. Similarly, 1 dot minus 1 also minus 1. 1 dot I equals to I. 1 dot minus I equals to minus I. Similarly, minus 1 dot 1 equals to minus 1. I dot I 1 equals to I. Minus I dot 1 equals to minus I. Therefore, 1 is the identity element. Now, the inverse element of 1 is 1, since 1 dot 1 equals to 1. Similarly, inverse element of minus 1 is also minus 1. Then minus 1 dot minus 1 equals to 1. And inverse element of I equals to minus I. Then I dot minus I equals to 1. Similarly, minus I dot I equals to 1. So therefore, an inverse of minus I equals to I. Then hence, all elements of G, we get inverse elements that also belongs to G. So therefore, from first four conditions, we show that G is a group. Now again, if we taking multiplication of any two elements, I dot minus I here, that equals to minus I dot I, that equals to 1. So therefore, if we taking any two element and we multiplication of these two elements, we show that both are same. So therefore, dot, the multiplication is commutative here. Hence, G comma dot, it forms a commutative group. Now we discuss about permutation group. For discuss permutation group, first we know what is permutation. Let X be a non-empty set and a permutation is a mapping. Permutation is a function from X to X, and this function may be 1, 1 and 1, 2 function. If we take an example, X equals to this n number of set A1, A2, dot dot an, be a finite set, must be finite set having n elements. Then pi is a from mapping from X to X, function from X to X, be a bijective function, and this bijective function defined by in this way: pi I ai equals to bi. That means image of ai in bi. Or then the permutation pi can be written as pi a1 image pi a1, a2 image pi a2, dot dot a1 image pi a1. Or we also write down pi equals to a1 image b1, a2 b2, dot dot an bn. Next, multiplication or composition of permutation. Let pi 1 equals to this permutation a1, a2, a3, dot dot an, corresponding pi a1, pi 1, a2, pi 1, a3, dot dot pi 1 an. And another permutation pi 2 equals to a1 also mapped to pi 2 a1, a2 mapped to pi 2 a2, a3 mapped to pi 2 a3, dot dot an mapped to pi 2 an. P2 permutation defined on the set of X equals to this a1, a2, an. Then the composition of pi 1 and pi 2 is denoted by pi 1 small circle pi 2 and defined by this pi 1 small circle pi 2 equals to first row element a1, a2, a3, an, and this equals to composition pi 1 of pi 2 a1, pi 1 of pi 2 a2, similarly pi 1 bracket pi 2 a3, pi 1 bracket pi 2 a1. That means first pi 2 map a1 to some element, then pi 1 map. For example, pi 1 equals to 1, 2, 3 and 1 map to 1, 2 map to 3, 3 map to 2. Or sometimes you write down which we also tell pi 2 equals to 1 image 2, 2 image 3 and 3 image 1. P2 permutation defined on the set 1, 2, 3. Then pi 1 composition pi 2 equals to, this must be same 1, 2, 3 domain set, and Therefore, first pi1, pi2, that means pi2 first map, that pi2 1 map to 2, again 2, again pi1 map, that pi1 2 map to 3, that means pi1 composition pi2 1 map to 3. Second, pi1 composition pi2 2 map to, that means first pi2 2 map to 3, next 3 map to 2, that means 2 map to 2. Next pi2 3 map to 1 and 1 map to 1, that means pi1 composition pi2 3 map to 1. Similarly, pi2 composition pi1 equals to 1 to 3 and 1 map to 2, 2 map to 1, 3 map to 3. Now, identity permutation. A bijective function I from the set x to x is defined by this way: I a1 ai equals to ai. That means identity permutation maps same element to same. That means ai map to ai. Or similarly also tells image of ai equals to ai for all I equals to 1 to dot dot n, each called identity permutation, and we write down identity permutation in this way. And next we define the inverse permutation. If we taking pi, a permutation from x to x, okay, then pi is a bijective function, and any bijective function we know there is a inverse function exists, pi inverse. This is also map. This is also function from x to x, and pi inverse is also bijective. Thus, pi inverse is a permutation on x, and we also know from function of mapping composition, pi composition pi inverse that equals to pi inverse composition pi equals to I. And inverse permutation we write down in this way: if pi equals to this, then inverse of pi inverse we write down just interchanging. Pi a1 map to a1, pi a2 map to a3 dot dot pi an map to a1. That means domain set and codomain set just interchange. Now we define cyclic permutation. Let pi be a permutation on the set x, this a1 a2 dot dot an, defined by this way: pi ai that equals to ai plus 1, where I equals to up to m minus 1, and pi am equals to a1, and pi ai equals to ai, where I equals to m plus 1, m plus 2 up to n. Then this pi can be written in this way: a1 map to a2, a2 a3, a3 a4 dot dot am map to a1, and other terms m1 to m all are same. That means am1 map to m1, an map to an. Or we also write down pi equals to in this form. That means a1, a2, a3, an. That means a1 map to a2, a2 map to a3, a3 map to a4 dot dot am map to a1, and all other elements map to same element. That means in this element am1, other element, that means am1 map to am1, am2 map to am2 dot dot a, and also map to an. This permutation pi is called cyclic permutation, and cyclic of length m. For example, if we taking pi in this way, then here 1 map to 2, 2 map to 4, 4 map to 3, 3 map to 1. And therefore, this is a cycle permutation, and cycle permutation write down in this form: 1, 2, 3, 4. That means, and 5 map to 5, 6 map to 6. That means 1, 2, 3, 4. 1 map to 2, 2 map to 3. Sorry, we not write down this way. The cycle permutation we write down in this way: 1, 2, 4, 3. Sorry, we write down in this way, not in this way. 1 map to 2, 2 map to 4, 4 map to 3, 3 map to 1. Now, the set Pn of all permutation on n elements forms a group with respect to permutation, multiplication, or composition of permutation. We show that this. First, we consider a non-empty set X, a1, a2 dot dot n element set. Next, Pn the permutation. Permutation means a mapping f from x to x, and this mapping or function must be 1 1 and 1 2 function. Now we consider three function f, g, h, an element of Pn. That means these f, g, h are a 1 1 and 1 2 function from x to x. Now first we know that the composition of two bijective function is also a bijective function. Hence, F composition G, this must be a 1 1 and 1 2 function. Therefore, F composition G must be an element of Pn. Therefore, composition of function defines a binary operation in Pn. Second property, associative property. We also know that composition of function is associative. If we taking any three function, then we taking this type of composition, F composition G, again composition H, and G composition H first, then composition of A. Both must be same in function. Therefore, this operation composition is associative here. Now, the identity function I from x to x defined by this way, ai equals to ai for all I equals to 1 2 dot n. This is also a 1 1 and 1 2 function, and for this function this property always hold, a composition I that equals to f that equals to I composition f. For all f must be an element of Sn. So therefore I is the identity permutation. Now next, f is a 1 1 and 1 2 function, then F inverse must be exist, and F inverse defined by from x to x, and this is the defined F inverse ai equals to aj, where F aj equals to ai. This way we define F inverse for all I equals to 1 2 dot dot n. This is a 1 1 and 1 2 function. So for each f comma pn, that means f in pn, F inverse, we get a F inverse in Pn, and this condition must satisfy. That means F inverse composition F that equals to I, also F composition F inverse. So every element in Pn have a inverse in Pn. So every element in Pn have a inverse in Pn. So therefore, all the property, first composition is a binary operation. Second property, associative property. Third property, identity element exists, and fourth, inverse element exists. Therefore, Pn comma composition, that means permutation composition is a group, and this group is not a permutation group on an element. Now we discuss is S3 comma composition. That means here S3 is the set of all permutation on this set I3 equals to 1 to 3. So here we consider the set just only 3 element 1 2 3, and composition is the product or composition of permutation. This cycle is the product and composition of the permutation. So here S3 the set of all permutation on I3. Therefore we define S3 equals to in this way: alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. And where alpha 1 equals to 1 to 3, 1 map to 1, 2 map to 2, 3 map to 3, first alpha 1. Second alpha 2, 1 map to 2, 2 map to 1, 3 map to 3. Alpha 3, 1 map to 1, 2 map to 3, and 3 map to 2. Alpha 4, 1 map to 3, 2 map to 2, 3 map to 1. Alpha 5, 1 map to 2, 2 map to 3, 3 map to 1. And alpha 6, 1 map to 3, 2 map to 1, 3 map to 2. That S3 contains 6 elements, and we know if we taking any we know all function from a set is or any type of set contain 3 elements, then number of elements, number of function 1 1 and 1 2 function equals to, if any set is that contains n element, if any set contains n elements, then all 1 1 and 1 1 function and 1 2 function equals to that. So then the number of 1 1 and 1 2 function equals to n factorial. And in this set, S3 is the all permutation. That means all 1 1 and 1 2 function on the set I3. Now I3 contains 3 elements. Therefore, number of 1 1 and 1 2 function are 3 factorial. That means 6. Therefore, S3 contains 1 2 3 6 element only. Now we form the following composition table. In first row, we write down alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, and corresponding in column, we write down alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. And this is the permutation combination symbol. Now, alpha composition alpha equals to alpha, alpha composition alpha 2 equals to alpha 2, alpha 1 composition alpha 3 equals to alpha 3. Similarly, if we taking all composition, we get this from this table. Now, we taking how we write down this, that means composition. Now, we calculate the composition. How we write down composition? First, if we taking any arbitrary alpha 2 equals to, first we taking alpha 2, that means 1, 2, 3, 2, 1, 3. And alpha 3 equals to 1, 2, 3, that equals to map 1, 3, 2. And therefore, alpha 2 composition alpha 3, 1, that maps to kya? That maps to alpha 2, alpha 3, 1. Now, alpha 3, 1 map to 1, so therefore alpha 2 of 1, that equals to, and alpha 2, 1 map to 2, so therefore alpha 2 composition alpha 3, 1 map to 2. Similarly, alpha 2 composition alpha 3 of 2, that equals to alpha 2 map alpha 3, 2. Now, alpha 3, 2 map to 3, that equals to alpha 2, 3. Again, alpha 2, 3, 3 map to 3, so therefore that equals to 3. So therefore, alpha 2 composition alpha 3, 2 map to in the point 3. Similarly, alpha 2 composition alpha 3 of 3, that equals to alpha 2 of alpha 3 of alpha, alpha 3 of 3, that equals to alpha 2, 3 map to 2, so therefore alpha 2, 2, and alpha 2, 2 map to 1, so therefore 1. So therefore, alpha 2 composition alpha 3 equals to 1 map to 2, 1 map to 2, next 2 map to 3, 2 map to 3, next 3 map to 1, 3 map to 1, and this equals to alpha 5, 1, 2, 3, 2, 3, 1. You see here, this equals to alpha 5, 1, 2, 3, that equals to 2, 3, 1. Then this way we calculate the composition, alpha 2 composition alpha 3, that equals to alpha 2 composition alpha 3 equals to alpha 5. Similarly, we are taking another part, alpha 2 composition alpha 5. And alpha 2 equals to 1, 2, 3, corresponding to 1, 3. Similarly, alpha 5, 1, 2, 3, 2, 3, 1. Now, alpha 2 composition alpha 5 of 1, that equals to alpha 2 of alpha 5 of 1. Now, alpha 5 of 1, that map to 2, that equals to alpha 2, 2. Again, alpha 2, 2 map to 1, so therefore, alpha 2 composition alpha 5, 1 map to 1. Similar, next, alpha 2 composition alpha 5 of 2, that map to alpha 2 of alpha 5, 2. Now, alpha 5, 2 map to 3, so therefore, alpha 2 is 3. Again, alpha 2, 3 map to 3, so therefore, that equals to 3. That means, alpha 2 composition alpha 5, this 2 element map to 3. Alpha 2 composition alpha 5 of 3, that equals to alpha 2 of alpha 5 of 3, and alpha 5 of 3, that equals to 1, alpha 2, 1, again alpha 2, 1, that maps to 2. So therefore, alpha 2 composition alpha 3, that equals to 1 to 3, and corresponding 1 corresponding to 1, and 2 corresponding to 3, and 3 corresponding to 2, and this equals to alpha 2, 3, and this equals to alpha 3. Therefore, alpha 2 composition alpha 5 equals to alpha 3. So in this way, similarly, we calculate in this composition table. Now, from this composition table, we first, if we taking any two element, alpha 1 and alpha 1, and we use the composition of any two element, then we, from this table, you see that this must be an element of S3. Okay, therefore, permutation composition is a binary operation on the set of S3. This is the first property. And second property, associative property. And we already know that if we taking any Pn, that means all permutation on the set of n elements. This is associative. And we know that if a large set holds a property, associative property, then a subset of this must also must hold the associative property. Therefore, associative property also hold in S3. Now the identity element. From this composition table, we clearly see that alpha 1 is the identity element. Since alpha 1 composition alpha 1 that equals to alpha 1 composition alpha 2 equals to alpha 2, alpha 1 composition alpha 3 that equals to alpha 3, alpha 1 composition alpha 4 equals to alpha 4, alpha 1 composition alpha 5 equals to alpha 5, alpha 1 composition alpha 6 equals to 6. Similarly, from this table. Therefore, we clearly see that alpha 1 is the identity element. Now, fourth property, that means the inverse. Now, from this table, we clearly see that alpha 1 is the inverse of alpha 1, that means self inverse. Alpha 2 composition alpha 2 equals to alpha 1, that means alpha 2 is inverse of alpha 2 itself. Alpha 3 composition alpha 3 equals to alpha 1, that means alpha 3 has self inverse alpha 3. Alpha 4 composition alpha 4 equals to alpha 1, that means alpha 4 also has self inverse. Now, alpha 5 composition alpha 6 equals to alpha 1, and alpha 6 composition alpha 5 equals to alpha 1. That means alpha 5 is the inverse of alpha 6 and alpha 6 is the inverse of alpha 5. Therefore, from this table, we clearly see that all elements have inverse. Therefore, S3 comma composition, that means product or composition of permutation, is a group. And the number of element in S3 equals to 6. Therefore, this is a group of order 6. Therefore, this is a group of order 6. We write down. Now, we also check non-abelian or non-commutative condition. For a commutative condition, that means condition that equals to, if we composition any two element, the alpha 2 composition alpha 3 equals to alpha 5 here, and if we taking alpha 5 composition alpha 3, alpha 5 composition alpha 3, that equals to alpha 2. Therefore, alpha 2 composition alpha 3, that equals to alpha 5, and alpha 5 composition alpha 3, alpha 3 composition alpha 2, alpha 3 composition alpha 2, that equals to alpha 6. Therefore, these two are not same. Therefore, this is not abelian. Therefore, S3 composition is a non-abelian group. Thank you, everyone. In next lecture, we discuss about details of the group, some another theorems and properties.